Have you ever wondered how a simple, curved piece of glass can let us see galaxies light years away? Or how a camera lens can freeze a perfect moment in time? Well, the secret is all in the physics of light. Today, we're going to break down the essential formulas of ray optics. This is your ultimate guide to understanding how we see and how we manipulate the world through mirrors and lenses. So here's our game plan. We're going to start with the two absolute fundamentals, the laws of reflection and refraction. Then we'll get into a really cool trick called total internal reflection, basically how to trap light. From there, we'll master the math for mirrors and lenses, use that to build things like microscopes, and then at the end, we'll put it all together in a handy formula sheet that'll make you an optics pro.
Okay, let's just dive right in. Everything in optics, and I mean everything, boils down to two incredibly simple rules that tell us what happens when a ray of light hits any surface. If you get these two, you've got the foundation for everything else we're going to talk about.
First up, we've got reflection. Like what happens with a mirror. It's so beautifully simple. Imagine a line that's perfectly perpendicular to the mirror's surface, right where the light hits it. We call this line the normal. Well, the angle the incoming light ray makes with that normal line, that's the angle of incidence, is exactly the same as the angle the bouncing ray makes. It's simple, it's elegant, and it's perfectly symmetrical.
But what if light doesn't bounce? What if it passes through something, like from the air into a pool of water? That, my friends, is refraction. The light ray actually bends. And Snell's law here tells us exactly how much it's going to bend. The secret ingredient in this formula is N, the refractive index. You can kind of think of it as a material's optical friction. Air has a low N, but water is more optically dense, so it has a higher N. When light enters that denser medium, it slows down a bit and bends toward that imaginary normal line. This simple bend is the powerhouse behind every single lens.
So, we know that light can bounce off a surface or can bend through it, but what happens if we push that bending to its absolute limit? Well, we get this amazing phenomenon called total internal reflection, where we can literally trap light inside a material. Now, this only works when light tries to go from a denser medium, like water, back into a less dense one, like air.
Imagine you're underwater with a flashlight and you point it up at the surface. At a shallow angle, the beam escapes into the air, bending away from the normal. As you increase that angle, it bends more and more, until you hit a very special angle, the critical angle. At this exact point, the light just skims right along the surface of the water. Now here's the magic. If you increase your angle just a tiny bit more, the light can't escape at all. It's perfectly reflected back down into the water. It's trapped.
And this isn't just some weird physics trick. We use it everywhere. It's the reason a well-cut diamond sparkles so much. Light gets trapped inside, bouncing around a ton before it finds a way out, creating that brilliant fire. It's also the fundamental principle behind the fiber optic cables that give us high-speed internet. Light signals reflect perfectly down miles and miles of thin glass fiber without losing their strength. All right, now that we've got the basic rules down, let's see how we can actually use them to build things. This is where mirrors and lenses come into play. By giving a surface a very specific curve, we can control how light reflects or refracts to focus it and create images. But to do this with any kind of precision, we need a consistent set of rules for our math, a kind of golden rule book. Okay, I need you to pause and really focus here, because this is the golden rule for every single calculation we're about to do. It's called the Cartesian sign convention. First, we always assume light travels from left to right. Second, all distances are measured from the center of the mirror or the lens. Now for the signs. Any distance measured in the same direction as the light is positive. Any distance measured against the direction of the light is negative. And for heights, anything above the main axis is positive and anything below is negative. Get this down and the formulas become foolproof.
Let's kick things off with mirrors. This beautiful little equation connects three key distances. You've got u, which is just the distance of your object from the mirror. You've got v, the distance of the image from the mirror. And you've got f, the focal length, that special point where parallel rays of light all meet up after reflecting. And for any spherical mirror, the focal length is simply half its radius of curvature.
Okay, let's try this out with some real numbers. We have an object 15 centimeters from a concave mirror. So following our sign convention, we measure from the mirror against the light to get to the object, which means u is -15. A concave mirror focuses light in front of it on the against the light side, so its focal length f is also negative, -10. We plug those into our equation, solve for v, and we get -30 centimeters.
So what does that negative sign tell us? It means the image is also formed on the against the light side, 30 centimeters in front of the mirror on the exact same side as our object. See? The signs tell the story.
Now, before we can build the formula for a whole lens, which remember has two curved surfaces, we need the formula for just one. This equation here describes what happens when light passes from one medium to another through a single curved boundary. It might look a little complicated, but just think of it as the fundamental Lego brick. Once we understand this piece, we can stick two of them together to build the much simpler and more useful lens formula.
And here they are, the stars of the show for lenses. The thin lens formula looks almost identical to the mirror equation, right? But just look closely. Notice that crucial minus sign instead of a plus. But the really powerful tool here is the lens maker's formula. This is like the actual recipe that lets an engineer design a lens from scratch. It tells you that if you know the refractive index of your glass and you can precisely grind the curves of its two surfaces, you can create a lens with any focal length you want. It's how we design everything from eyeglasses to massive telescope lenses.
Let's run a quick example with the thin lens formula. We've got an object 20 centimeters away, so U is -20 since it's measured against the light. It's a converging lens which has its focal point on the far side in the direction of the light, so its focal length f is positive, +10. We plug them in, solve for v, and we get +20 centimeters. That positive sign is the key. It tells us the image is formed in the direction of the light, on the other side of the lens.
So you've probably heard your optometrist talk about diopters when you get your eyes checked. Well, this is it. The power of a lens is just the inverse of its focal length. The only catch is that you have to make sure the focal length is in meters, not centimeters. It's just a really quick way to describe how strongly a lens can bend light. A higher power means a shorter focal length and more bending ability.
Here's a quick cheat sheet that makes life so much easier. Converging lenses, the ones that are thicker in the middle like a magnifying glass, will always have a positive focal length and a positive power. Diverging lenses, which are thinner in the middle, will always have a negative focal length and a negative power. Just remember this little table and you'll nail the signs every time.
Okay, so we've pretty much mastered the formulas for single mirrors and lenses. Now for the really cool part, combining them. By strategically placing lenses together, we can build instruments that let us see the incredibly small world of a cell or the incredibly distant world of a planet.
So the simplest optical instrument of all is just a magnifying glass, a single converging lens. Its magnifying power tells you how much bigger an object appears to be. The formula is 1 + d over f, where f is the focal length and d is what we call the least distance of distinct vision. For a typical human eye, that's 25 centimeters. It's basically the closest you can comfortably bring an object to your eye and still keep it in sharp focus.
Now, to get really high magnification, we need a compound microscope. This uses two converging lenses. The first one, the objective lens, creates a magnified, real image of the tiny object you're looking at. Then, the second lens, the eyepiece, acts like a magnifying glass for that first image, blowing it up even further. The total magnification is basically the product of the two, which lets us see into the hidden world of things like cells and bacteria.
And to see things that are really far away, we use a telescope. What's amazing here is just how simple the core principle is. The magnifying power of a basic telescope is just a ratio. The focal length of the big objective lens that gathers all that faint light from the stars, divided by the focal length of the small eyepiece you look into. That's it. So if you want huge magnification, you just need an objective lens with a really long focal length and an eyepiece with a really short one.
All right, we have gone on a journey from a single ray of light all the way to the design of a telescope. Let's take a second and boil all of that knowledge down to the absolute essentials. These next couple of slides are your quick reference guide, the ultimate formula sheet for ray optics. So here are the absolute fundamentals. We started with the perfect symmetry of reflection, angle in equals angle out. Then we had Snell's law, the engine of refraction that tells us how light bends when it crosses a boundary. And finally, that formula for a single curved surface, the essential building block for every lens we can make.
And here are the workhorses, the tools of practical optics. We've got the mirror equation and the thin lens formula. Just always remember that crucial sign difference between them. Then there's the simple definition of a lens's power in diopters. And finally, the rule for combining lenses, which shows how their powers just simply add up when they're placed together. From a simple reflection all the way to the complex design of a telescope, these formulas are the language that we use to understand and control light. They are the toolkit that has allowed us to explore the entire universe, from the cellular level all the way out to the galactic. So, now that you have the toolkit of light, what would you build?